Jeff Ronius on Twitch says, full-time Rust work is your 5-year plan. It's encouraging to see a company actively looking for a Rust engineer. And Mr. Halsey also says hi. Mr. Halsey is a prolific words. He streams a lot. And he does a lot of game development on using Rust and what is it? It's not Unity. It's the open source competitor to Unity. It's
Godot or
Godot. We're using the Rust plugins. Yeah, I got lots of now corrections in chat for that. But anyways, like there's a really good Rust community on Twitch. If any of you want to watch live programmers, hacking with Rust. But we're not here to talk about that today. We're here to talk about machine learning. So I don't have like a super great introduction for Vlad. So Vlad, I'm going to hand everything over to you to talk about machine learning and take it away.
Thanks, Rooks. I don't have a good introduction as well, so let's see. So today's presentation, I don't know whether you can see my screen or not.
Yes, I can see it.
Okay, sounds good. So the presentation, in this presentation, well, first of all, my name is Vlad Orlov, and I work as an engineer in PayPal, where we personalize everything we can. I've been engineer for, I don't know, 10 years. I'm an open source contributor. And today I want to talk about some basic machine learning ideas and how would you go about implementing some very simple algorithm from scratch in Rust. The goal for today is to build two basic machine learning algorithms, like a simple regressor, simple classifier, using just Rust, and some of the libraries that are out there that have been that are mature, that have been written by other people that have been there for at least a couple of years, and one unit library that I'm contributing to. So before we jump into that, a couple of disclaimers. First of all, I gave this talk already at the end of last year. Well, it wasn't the same talk, it was a similar talk. But if you've seen the slides, there's not much of a new information, unfortunately for you. If these slides are new for you, that's great. Stay tuned. And another disclaimer is that, well, you should be on board with this idea that Rust is great for scientific computing. If not, I really recommend to read this article in Nature. It's kind of a motivational article for anyone who is doing science or just interested in Rust or scientific computing. It's all about one guy using Rust for his simulation that he is trying to do. And it's a great motivational article, as I said. In this presentation, I'm not talking about deep learning, partially because I haven't tried to do it myself in Rust. And I think that well, if you'll try, you'll find a lot of example tutorials around this topic. So I'll leave it to someone else to talk about deep learning. I'm not going to talk about large machine learning. What I mean is, frameworks like Spark, Deep, other frameworks that can distribute your computation across multiple machines in a cluster. And also, I'm not talking about accelerators. So all of these topics, if somebody wants to talk about these, let me know. I mean, just let Brooks know, and yeah, that would be interesting to. I would be interested to hear someone talking about that as well. If you don't have a prior exposure to machine learning, here's a quick refresher on basic concepts that we'll need for today to go into the code. So first of all, let's answer the question: what is statistical learning? So let's say we have our data set, and in this data set we observe a quantitative response y. And in this data set we have a bunch of predictors, a bunch of variables. So for example, you might have a data set with lots of houses, and each house has attributes like number of rooms, number of bathrooms, whatever. And what you're interested in predicting the price of the house. So what we are in machine learning, what we do most of the time is we first of all we think about this relationship. What's going to be a relationship between our target variable, which is in this case it's a price of the house, and predictors, which in this case are all the attributes that you can extract from the data. So here's an example. For example, we can have a data set like this. That's just the first 5 rows of the Boston housing data set. And on the left, we have attributes of the house. On the right, we have the price that we're trying to predict. And that's a very old data set. So the price, I don't know, it doesn't make sense to me, but for us, for our purpose, it's just a number that we're trying to predict. The usefulness of such a model is that you can once it's fully trained, and if it's accurate, if it's good, it can predict, it can extrapolate, it can predict a price of the house from the new data. So usually when you when we do statistical modeling, we are trying to solve some concrete problems, and there are multiple ways to categorize these problems. For example, if you have a house price in your data set, this type of the problem in machine learning, they call it supervised learning, because you're supervising your model when you're training it. You're telling your model what's the right price of the house. Versus in unsupervised learning, we don't have our target. We don't know what's the right price for the house. And in this type of learning, what we're trying to do, we're trying to see what are the patterns in our data that might be useful for us, or how can we split our data into multiple clusters, or maybe even how we can what common features we can extract from this data set that can be used down the road to in some other processes and programs. The other categorization that I want to talk about is the type of the target, the type of the target variable that we have. If it's a quantitative variable, then all we can build is a regressor. Basically, we are predicting a number in this case. If it's qualitative, if it's a category, we call it a classifier. So today we're going to build a classifier and a regressor. And the other thing that I want to say is that when you're choosing the model or trying to answer this question, what type of model will be better for your data? What parameters for your are there for you? What are the best parameters for your model? How can we estimate these parameters? These are the all the basic questions that you ask yourself when you develop a statistical model. And when you solve a machine learning problem, first thing you will try is to understand what category this problem falls into. Is it a classifier? Is it a regressor? What kind of existing algorithms can I use in my data? And to answer all of these problems, you will need a library that you can use to try different relationship between X and Y. And the languages like Python and R provide a vast ecosystem of tools that can be used by machine learning engineers and data scientists to quickly fit different relationships, different types of models to the same data, and to see which one works better. All of these tools that we're talking about, all of these libraries like scikit-learn, I don't know, SparkML, TensorFlow, they use tools, mathematical tools that have been developed already in, I don't know, and are still being developed. But that's not something new. So you can roughly, think of 4 branches of mathematics that that machine learning is based upon. That's a loosely speaking, of course. So maybe there are more, but in my opinion, that's the when you're looking for a language for support, for the language that provides a good support for machine learning, either it's in Rust or Python or any other language, what you're looking for are libraries and ecosystem that covers all of these basic branches. And the good news is that in Rust, you will find good crates that cover 2 of these at least. And I'm going to touch upon some of these libraries today. And the just for I can't talk. I can present. For this presentation, I have to pick some concrete algorithm to talk about. And the type of the model that we're going to talk today is a linear model. One reason is because it's a very simple model to explain, and the other reason, of course, is because it's a very powerful type of the model that is being used in a lot of scenarios. For example, in PayPal, it's one of the logistic regression is our to-go model for a lot of scenarios where we want to personalize something. Especially when it comes to building an ensemble of models, we tend to use logistic regression just because it's a very simple thing to implement, and it's a very fast when it comes to training this model on a big data set. So what is the linear model? In essence, it's just a line or a hyperplane that approximates this relationship between your predictors X and your target Y. If we have just one variable, if we have just one variable, by the way, do you guys see the black the Zoom the list of the participants in Zoom that I see or not? I'm not sure about that.
Not in your screen sharing, no.
Oh, that's great. Yeah, because kind of on my way, and I'm thinking maybe you guys can see too. But that's great. So back to the linear model. If we have just one predictor, let's say we have just one X, it might be a height, for example. Then with the linear model, what we do when we predict, let's say, weight from this height, we just look where the vertical line that goes from X intersects our line, and this point where it intersects is our predicted value, is our Y. So it's as simple as that, And of course, when you have many multiple predictors, like when your axis is not just one predictor but many, this line becomes something more complex. It becomes a hyperplane. But the basic formula that you use to make a prediction is just a matrix multiplication between the predictors, the attributes that you've extracted from your data, and some parameters of your model beta. And what are these parameters? It's these parameters define this plane, this hyperplane, or a line if it's just in 2D. For example, in 2D, these parameters would be beta 0, which is this intercept where that this point on y where this line intersects y, and b1 would be the slope of this line. In multiple dimensions, when your axis has multiple attributes, as I said, this line becomes a hyperplane. So you have many parameters. So your beta is a vector, and your x is a matrix. And by the way, this matrix has the dimension, the dimension of this axis, n by m, where n is a number of columns, number of samples in your data, and m is the number of predictors. So if we go back here, so here the matrix will be, we have 13 attributes extracted from our data set, and the rest is this matrix will be tall and skinny, so to speak. We'll have many instances, many houses in our training set, and few parameters. Now let me switch to some code. First of all, I want to walk over the a typical scenario. How do I fit something as simple as a linear regression in Python to a Boston housing data set? First thing first, I think I need to, oh, okay. So let me see. Okay, so let me first load the data. And here, by the way, I'm using some of the standard tools provided that comes in that everyone who uses Python has to deal with when it comes to machine learning. So you first of all, we need to load the data as a data frame. When I load this data and display it, we see the similar table that I've already shown to you. The other thing that I'll need to do, I'll have to take this data frame and split it into predictors and the target. The way I do that is, of course, I'm using some of the built-in data frame functions to extract just the attributes and to extract the target. And I just to check everything is fine, I'm printing out the shapes of the data here. So next, the other important step that I would do every time I feed a model in Python, I would split this data set into training and test sets. Why I'm doing that is because I want to make sure that the error that I'm estimating, because every model is not ideal and every model will have some error. By the way, that the error in this formula, the error is this component here, this epsilon. It's an error. It's something that I cannot get rid of with my model, because my model is not ideal. My model, all of my data points they will not end up being on my hyperplane or on my line. I will have some irreducible error, and to estimate this error correctly, I need to split my data into training test and the test set. And that's what I'm doing here. So I'm leaving 20% of my data for testing, and the rest I'm going to use for training. In Python and scikit-learn, that's the tool I'm using for machine learning right now. Fitting a linear regression is a very straightforward exercise. What you're going to do, you just make the call to a fit method defined on the linear regression, and this method takes your training data set, training labels, and gives you back a model. And the parameters of this model, these betas, I hope I have those parameters here. Yeah, so the parameters of the model are, they are estimated at this point. So at this point, you find what are the best parameters that fit your data, and you store it inside an instance of LR. And then what I'm going to do, I will take my model. I will use this formula to estimate the error. And this formula, it's a fairly straightforward thing. What we are doing here, we are for each predicted instance from our test set, we are comparing the predicted price. Well, actually, here this one, the predicted price with the true price, because our training set also has some has the price of the house. So the bigger this number, the bigger error I've got. So if we have the really small MSE, mean absolute error, that means we've got a great model. This number that I've got here, it doesn't tell me a lot because I haven't compared it to some other methods that I would use on this data set. But the idea is that now that we have some number to compare our the model that we've got in Python, let's try to build something similar in Rust. The question is, how can we do that? Because while there are some libraries in Rust that can do something similar, that you can use to make a call on the linear regression to fit your model. What ideally we want to do, I mean, the goal of this presentation is to show how to do it in pure Rust without using any of these libraries. And for the linear regression, there are multiple ways to find the estimate of parameters, of the model parameters. So one way is to use the linear algebra for that. And if you remember, so this is our equation, right? This is our equation. We are trying to find the model that we are trying to estimate parameters, this beta here. And X is a matrix, Y is the vector, beta is the vector. And from the linear algebra, you might remember this big chunk of the linear algebra is about solving equations like this. And you might remember this, how to do it. You basically need to find the inverse of the X. Well, here I've switched to different letters for, instead of X, I'm using A, instead of B, instead of beta, I'm using B. But actually, instead of beta, I'm using X. Instead of X, I'm using A. I probably need to fix that, but the idea is that we need to find the inverse of X. And frankly, first of all, that's not a straightforward thing to do. There are some methods and actually there are some libraries that, for example, Python uses to do that. But you don't want to implement that yourself. So ideally, what you want to have is some kind of a library that can do that for you. Another problem is that in many cases, you won't find an inverse of X. It's just not possible because you have a tall and skinny matrix. So what do you do instead? You multiply. You want to take your rectangular matrix and turn that into the square matrix. And the way you're going to do that is by multiplying X by X transpose. And that's what this formula is about. That's how you can find estimate of your parameters. So, let's try to do that in Python really quick. So what I'm doing here, I'm basically taking my training data and I'm preparing this training data. I'm splitting it into A and B. And then what I'm gonna do, I'll just apply this formula directly to my data, and then I'll print out these coefficients. And if what you might have noticed is that these coefficients that we found, for example, this 37, 0.3, is exactly the same. Actually, let me go back. It's exactly the same coefficients that we found with the scikit-learn library. So just using this method will give us exactly the same estimates as we've got in Python with the scikit-learn. And the question is, can we do the same in Rust? And the answer is, of course, yes. But we'll have to use some tool to take the inverse, because all this computation boils down to this call, this inverse. It's a very important call here. Without this inverse, you'll have to implement, you'll have to figure out how to do it yourself, because it's not a straightforward exercise to take this inverse. And also you want to do it fast, right? You don't want to this function to be inefficient. And luckily for us, we do have we do have two libraries in Rust that can take inverse of the matrix for us. I'm talking about an algebra and NDRA. And both of these libraries, they provide a very similar functionality. So in fact, while there are differences between these two, for example, an algebra, it is built primarily for different purpose, and it supports only 1D and 2D arrays, while the ND array is a bit more more flexible in this sense. And also, the good thing about an algebra, at least for demonstrations like this one, is that you don't have to, you don't need BLAS on LAPACK to solve the linear equations. You can just take the, for example, when it comes to inverse, you can just do it in pure Rust. You don't need to think about any accelerators that are out there. So compilation tends to be a little bit easier when you're working with an algebra. And I don't know, should I check the, does anyone has any questions or comments or anything you want to add to the presentation?
Not really so far. I've been enjoying this. This has been interesting. I have a Python data science background a bit, so it's been interesting watching this.
So does that mean that ND array is like a little bit like NumPy, where it's sort of just a front end for these BLAS and LAPACK libraries?
I would say it's more than ND array. Some of the methods that you will find there are implemented in pure Rust. Some of the more complex methods like inverse and stuff, they use they use it as a thin wrapper on top of LAPACK.
Between an algebra and ND array, what's your favorite?
I would say ND array. I prefer ND array because you know, they have a bit more straightforward system of traits. For example, what you can do with ND array is define, for example, if you want to extend this library or integrate with this library, you can define your methods in terms of the base array. I think it's called base array, some very high level trait that they define. And the good thing is that once you've defined your methods or integrated with this trait, all the other concrete implementations, implementation of this trait will work with your methods. So definitely ND array. But you know, I think an algebra in terms of working with, and the other, of course, difference is that the big difference is that if you go beyond two dimensions, if you need bigger matrices, actually tensors, if you need to work with arrays that are defined in multiple dimensions, you just can't do it in algebra. The only problem is this, BLAS-LAPACK. Sometimes it's a pain in the ass. For example, I tend to write my code in Mac, and it's kind of compiling that is not straightforward exercise. So let's see how we can do that in Rust. How can we take the Boston housing data set and repeat all the steps that I've shown in Python? How can we do the same thing in Rust? And for this presentation, I'm going to use nalgebra, but you can do the same thing with NDArray if you prefer NDArray. So first thing first, of course, I need to load the data set. In this case, I'm loading this data set from the CSV file, comma separate value file. The parse CSV function, it's something that that is not there. You won't find this function in algebra, or in fact, you'll have to implement it yourself, but it's not hard to do that. And also I have an example in my code that I'll share later. So what we are doing here, we're basically just loading this file and then reading all the content of this file as an instance of D matrix. D matrix, it's a dynamic matrix that is defined on F64. And here I'm printing the shape of this matrix. So this matrix has 506 rows, 14 columns. 14 columns because we have 13 predictors and 1 target variable. So now that we have it, we need to split. We need to take out the rightmost column and assign it to separate variable. Let's call it y, and the rest will be our predictors x. That's exactly what I'm doing here. And the way I'm doing that is by using methods defined on an algebra. So one thing that you will find, one thing that is useful about using the an algebra or NDArrays are those matrix manipulation methods that you will need to use in order to shape your data or extract certain things from your data, or feature engineering. That gets very handy. And of course, when you do machine learning, a lot of time is spent on data transformation to make sure that the features that you extracted are the features you need and are all standardized or adjusted the way you need it. And it's much easier to do that with the with methods like when you can let's say take entire column extracted from the data frame like I did here, and then take this entire column, divide it by some number, and multiply by some other number, something like that, without using iterators. So that's one useful feature of NDArray or nalgebra. And here I'm just printing out the result. So now my y variable contains only target, and the x contains only predictors. And then what I'm gonna do, I will split my data into train and test sets. Unfortunately, NDArray and algebra doesn't do that for you, so you'll have to use some other library. The library I'm using is SmartCore. I'll talk about it later. Here I'm just making the call to the function. It's a very similar idea to the train test split in scikit-learn. You take your X and Y, and you split it into train test sets. So X train is your training predictors, Y train is your training target, and X test and Y test is for testing. And here I'm just printing out the shapes of this these data frames. And then what I'll need to do is I'll need to apply the same formula to find estimates of the parameters. You know, it's with an ND array or an algebra, it's a pretty straightforward thing. All you need is to call this tri-inverse on your A transpose A, and you know, and then to make a prediction, what you'll have to do is to take the estimates of your the estimates of your test data, of estimates of your parameters, of your model parameters, and multiply that. Actually, the prediction is, yeah, so the prediction is here. So that's, sorry, I was confused because, you know, I'm looking at this X hat and I'm trying to understand why I named it X hat. And now I remember why. So the reason why I have this postfix hat is because the X in this case, it represents the parameters of my model. And the hat is, it is hat because these are just estimates. The theory is that when we feed the model to our data, we don't know what are the true parameters of the model, but we can estimate those parameters using, for example, the formula that I've presented before. So once I found my estimates of the model parameters, I can use those estimates to make a prediction. And to make a prediction, I'm taking the new data. In this case, it's the X test. It's the testing set that I left to estimate the error, and I'm multiplying that by my model parameters, and that's also another part of the model. The coefficient and intercept are, you know, two parts of the model parameters that I'm using to estimate the house price. And then when I'm using mean absolute error to measure the test error, the number that I'm getting, it is very close to the number that I've got previously. Let me see what it was. And yeah, so as you can see, that's the mean absolute error that I've got in Python. And that's the mean absolute error that I've got in Rust. So the reason why these two numbers are different is because when I did the train test split, I've randomized my training and randomized my data. So as a result, I'm getting different train test split every time I'm calling the function that splits the data. So every time I'll run the code, this code or this code, I'll get different errors. But the important point here is that we've got the same, well, we've got the two numbers are really, really close to each other. That means that this method that we found, it actually works. Like we are finding the, we were able to feed the logistic linear regression to our data. And we've got the model that has the same performance as the similar model in Python. And the other thing that I want to talk about is, well, I want to just briefly mention that. So this formula that I've used here, in fact, in Python, if you look into scikit-learn how they do that, they don't actually use this formula. So instead, what they do, sorry, not this one. Anyway, I think, yeah, they don't use this formula to find model parameters. Instead, what they use are, first they decompose the predictors into different components. So they take this matrix and they split it into a couple of other matrices. And why they do that is, well, and after they've done that, they use different formula that to find the parameters of the model. And why they do that is because this inverse that we've been taking previously, it's a fairly complex procedure. Like first of all, it's hard to make it work on a large data set, and it's not as numerically stable as this approach, partially because you will, when you decompose your matrix and you take an inverse of R, this matrix R it has different structure, so it's easier to take an inverse of R than inverse of the A. That's why, you know, in scikit-learn and in other implementations where they fit linear regression to your data, they do decomposition first and then they find the model parameters by taking the inverse of R. Or if they use, in fact, you can use other methods to decompose your matrix. You can use SVD or LU decomposition. I think any decomposition method will do, but the formula might be different. So there's definitely, and by the way, there is a way to do that in Rust as well. Let me just show you an example. How would I do that in? Actually, maybe not. I don't think I have it actually. Surprisingly. Oh yeah, I think I do. So if you go with the nalgebra, the nalgebra also can do a matrix decomposition for you. So this method QR, it actually is defined in nalgebra, and I think NDRA has it too. But I think you'll have to use on top of NDRA. There's another library that is kind of part of the NDRA ecosystem that you'll have to define in the build. But the idea is that if your linear algebra crate can do matrix decomposition, that's great because now you can feed the linear regression more efficiently to your data. And that's all about linear regression. Now I want to switch gear and talk about the logistic regression. I think, well, smart core, let's talk about it later. So are there any questions or anything else? All right, so.
Oh, sorry, I had a question.
Oh, sure, yeah, go ahead.
Busy unmuting myself over here. How have you found using, it looks like you're using Jupyter like a Jupyter environment for Rust.
Mm-hmm.
How have you found that experience?
It's a bit weird in the sense that, you know, in Jupyter, when you're using Python, the last value that is that you instead of printing the last value, you can just say you can just define, you can just type the name of this variable. Let me actually show what I mean. So So for example, instead of printing the name of the variable, I can just type it here and press the run button, and it will show the content of this variable. So in Rust, if you do that, due to the memory management rules, what you do is you give the ownership on this variable to the kernel, to the method that prints it out, and you're losing an ownership. So next time when you try to use this library, let's say use this variable in, let's say, some other cell, you'll get a word error telling you that, hey, I can find this variable, you know, and just because of that, using the Jupyter Rust kernel for Jupyter, it's not as convenient as for Python. So I kind of recommend against it.
Yeah,
it's not as convenient.
Jupyter notebooks are amazing to, you know, get your feet wet in a language. And yeah, I thought it was really cool that you were running one for Rust, but obviously the ownership, you know, ownership sounds like it's kind of annoying to work around.
Yeah, that's why, for example, in a lot of places here, I'm doing this clone just to make sure that my variable is not being moved out from one variable. The value is not being moved from one variable to another. So instead, you know, in reality, this code can be a little bit cleaner if you don't do it in Jupyter Notebook.
Right. Cool.
But other than that, I think it's good for demonstrational purposes if you just want to write the code and then turn that into the slideshow like I did. It's very convenient.
Cool. Thanks.
So the final thing that I want to talk about today is the classifier. How would you write a classifier in Rust using the minimum number of crates? And once again, just to demonstrate the idea and some of the crates, I will use an extension of the linear regression, a logistic regression. The idea behind the logistic regression is that that you model the relationship between, well, first of all, if you remember in classification, what we do when we are writing a classifier, what we have is the target, and our target is a categorical variable. So instead of, for example, instead of a price of a house, we might have something like a probability, something like whether user has clicked or not. Or another example would be the transaction, whether it's fraudulent or not. You know, red or blue, spam, not spam. That's your target, and that's the only difference from the regression model. And in logistic regression, what we do, we model the relationship between our target, our categorical target, and our predictors the same way we did in linear regression. But now, since, you know, the linear regression, if we multiply our x by model parameters, we might get a number that, you know, is not, we will not give a number that is strictly 1 or 0. What we will get instead is the number that can be anything from, I don't know, minus really big number to plus really big number. And what we want to do is we want to make sure that this number is strictly between 1 and 0. So one way to do that is to use this sigmoid function that wraps our matrix multiplication. And because of this simple transformation, now we know that our predicted y would be always between 0 and 1. And then to make a prediction, what we need is to choose a threshold above which this our prediction is 1. And if it's not above this threshold, then it's 0. So for example, if we are trying to classify whether a transaction is fraudulent or not, we might set this threshold to, I don't know, 0.75 to make sure that we don't produce a lot of false positives. But now the problem that we have is, since we're using this nonlinear function, we can't use the same approach to find the parameters beta of our model as we did before. And in fact, previously I've shown you the method that scikit-learn, for example, uses to estimate parameters beta of the model from data. And that's not the only way, of course. The other way is going to be to use the optimization methods. And in Rust, there is a library that I want to talk about today. It's called the argmin, that has a lot of great optimization methods implemented for you. So what these optimization methods will do, they will help you to find the right estimates of beta. And I'll talk about it. I'll talk how to do that. But let's first, once again, go back to Python and just quickly fit the model to a logistic regression model to the credit card fraud detection data set. And I don't think I have the printout of this data set here, but let me see, maybe I do. Oh, actually I do. So when I load this data set in Python, these are the first 5 rows of this data set. We have 30 predictors. These are just some numbers that have been some features of the transaction. And that might be anything, I don't know, maybe how many times the user, the account value of the user, I don't know, number of times the user has transacted with this bank, and so on and so far. These numbers are just some numbers that we have, just some features of the transaction that we have extracted from a concrete transaction, and then we have a column with the class of the transaction. In this case, 1 tells us that the transaction is fraudulent, and 0 tells us that the transaction is okay. So what we're going to do, we're going to use this the same approach. We're going to split the data set into training and test sets, and then we will use logistic regression from scikit-learn to fit. We will fit logistic regression to this data, to the training portion of this data, and let's see how. And we will use another metric to estimate the performance of this model. And what this metric tells us, this number tells us, is that this model, this is a good model. It does a great job in separating the fraudulent transactions from non-fraudulent transactions. So basically, I don't want to talk about this metric, but the idea is that it gives us the number usually between 0.5 and 1. And we use it all the time when we are trying to see how good is our classifier. When I have a number that is close to 1, that means that my model, that I've got a great model. And when this number is close to 0.5, that means that my model doesn't do a great job in separating types, separating my data into doesn't do a great job. Once again, the question is, how would can I take the credit card transaction data and do the same thing, and take this data and feed logistic regression to my data using pure Rust. And as I said, the good news is that you can, but you will need this argmin library to do that. What this library provides, it provides the implementation of different optimization methods that you can use to estimate parameters of your model. And these methods, the selection of methods is, they have a really good selection of methods. They have methods that require that are gradient, based on gradient, and gradient free. And the other thing that I like about this library is that they support native vectors, native Rust vectors, and ND-array. So you can, if you're manipulating your data using ND-array, for example, you can just go ahead and use the all the methods defined in the argmin directly on your on instances, directly on the instances defined with the ND-array. And the other useful thing that I like about this library is that it provides the extensive logging and checkpoints. That becomes handy when you're trying to optimize, when your optimization method runs for a long time. So what you want is to make sure that that you save the state of the optimizer in between while the optimizer is running. If something has failed, you can restore, go back to the previous checkpoint as well to see what happened using this extensive logging. So these are kind of useful things to have. And let's see how we can do that, how we can use this argmin library to feed the logistic regression to our data. And once again, I'll use an algebra. I'll just quickly split my data, load my data, split it into X, Y, and then I'll do the train test split. And that's again my sigmoid function. Well, the other thing that I'll have to think about is, well, you remember this formula, right? It's just the our attributes, our transaction, our 30 attributes of a transaction multiplied by model parameters, and then the sigmoid function that we use to find the probability of whether this transaction is fraudulent or not. So other thing that you'll have to think about is this cost function. So what this cost function does for you, actually, why you need this cost function? You will need this cost function to for the optimizer. So the optimizer needs, think of optimizer as some kind of a search function. So what this optimizer is looking for, it looks for the parameters of your model that fit your data as best as it can. And this cost function, the goal of this cost function is to tell the optimizer how far it is from its goal. And the goal is to find those parameters, this best matching parameters. So what this cost function should do, it should return a small value when the optimizer have found the best parameters. And it should return a large value when this optimizer has failed to do so. So when the optimizer goes farther away from the best parameters in the search space, the value of this function should increase. And the value of the function should decrease when it goes to gets closer and closer to the target. And the good thing about using standard machine learning techniques like logistic regression, linear models, SVM, I don't know, generalized linear model, is that all of these methods, they come with the, so to speak, predefined. So it's not hard to find the cost function in the web. That's how I did that. This comes directly from the web. I didn't invent it myself, of course. The other thing that we'll need is this derivative. In fact, not all the methods in argmin require the derivative to find the best parameters. For example, there's a great method that I like to use when I can't take the derivative of a function. It's called CMAES. One example is when you're trying to optimize the hyperparameters of your model. You might want to look into that. You don't need derivative to find the to use this method, but today we're going to need the derivative as well, simply because the method that I'm going to use, it requires the cost function and the derivative to find the best matching parameters. And that's my sigmoid function. So that's how I defined it. It takes the result of the matrix multiplication, and it squishes this number between 0 and 1. It's just a direct application of this formula. So one way to demonstrate how this cost function works is just to try some numbers. So let's say that, so first of all, this cost function, what it takes your estimate of the your estimate of this probability. So what it does, it takes this estimate and it kind of uses this estimate to see how far is this estimate from the true value, from this y, from the true value, because in our training data set we have the true value. So let's say our true value is 1.0, which means that the transaction is fraudulent, and our model with the optimizer have found some parameters, and these parameters, when we use those parameters, we get a number that some very large number, and when we apply sigmoid function to this very large number, this sigmoid function will transform this number into 1.0. So in this case, we should get, since our estimate of the probability matches the true class of the transaction, the cost function should give us a small number, because in this case there was no mistake in estimating the true value of the true estimate, estimating the true value of the class. And as you can see, when we apply this formula directly to our values, we get some really small numbers. So what it tells our optimizer is that, hey, we found this great, I think it looks like we found good match. Looks like our parameters is a good fit to our data. On the opposite side, when we have when our model predicts 0, the cost function will give us some large value, and this will force our optimizer to look for better parameters. So that's and finally, what I want to show is how to actually use it in practice. So here we are defining some of the methods. We are using some of the methods defined in the argmin library the method that we're going to use to one of the optimizers that we're going to use is called LBFGS. It's the standard optimizer. If you look into the documentation of the scikit-learn logistic regression, you will find that they actually use a lot of they actually give you a choice of for the optimizer. So you can when you're fitting your model to your data, you can choose between different methods that you will use that the scikit-learn will use to find these parameters. And by default, they use LBFGS. So that's the method that I don't think it was created specifically to fit the logistic regression or linear models, but it's a very popular method to do exactly that. And the good thing is that, you know, in argmin, they actually do provide this optimization method as well as many others. So there's a good chance that you'll find the optimization method that you need in this library. And what we need to do, we need to define our loss function first. You know, here, while it looks a little bit ugly, it's basically this function that I've showed you previously. So it's, you know, it's this function here. And the gradient of this function, this guy here, as I said, we're going to need that because this particular optimization method requires gradient to do this work. Once we have our loss function, what we're going to do next, we're going to write another function that will be a driver that will drive our optimization. So what this method takes, it takes our training data set, training labels, and it produces the estimates of the parameters or an error. So here we define our loss function. We set up the optimization method here, and then we just say, okay, now run. And also we set maximum iterations. I don't know. It might be some really big number. Usually you don't. Usually a lot of the optimization method, they will terminate either when the method reaches this many iterations or when certain conditions are triggered. And this condition might be, for example, that the gradient is of the function gives us a very low, small number, or that the parameter values do not change that much from iteration to iteration. So in general, you don't want to set this number to some very large number, but it should be you know, sufficiently large enough, because if you set it something small, you will end up with suboptimal parameters for your model. So finally, when we run this method and we get our model parameters, we can use these model parameters to make our prediction. And our prediction in this case would be a straightforward application of the sigmoid and straightforward matrix multiplication. So first we are running this, we are using the same formula as we did in linear regression to estimate y hat, and then we squish this value to be between 0 and 1. And then we use this threshold of 0.5 to see whether or not this transaction is fraudulent or not. And that's pretty much it. So now to see how far we are in terms of the error, how good is our model, let's use the ROC. Let's use the same metric we use in Python to see the error. And surprise, surprise, we've got the error that is not far from the error that we are getting in Python, which tells us that you know, we can do a great job of fitting logistic regression in Rust using some very standard libraries, nothing from C++ Word, nothing from Python. Just in pure Rust, we can do the same thing that the scikit-learn does for us in Python. And Finally, what I want to say is that all these methods that I've demonstrated, using linear algebra, using ND-array and algebra to manipulate your data, using the argmin or similar library to optimize, to find the minimum or the maximum, the best fit for your data, the best model that fits your data, that fits your data. All of this method can be extended to other more complex machine learning algorithms. For example, in SVD, you're going to use something similar to the approach that I've used here to optimize to find the parameters of the logistic regression. And the other example would be the principal component analysis, where you take your data set and reduce the dimensionality, reduce number of dimensions from some large number. Let's say you have a data set like an image, and you want to compress that to just 2 dimensions. You would use, you can use ND-array or an algebra to do that yourself without without the need to call any Python or C++ libraries to do it for you. And that's pretty much it. Oh, I think there are some questions here. Any questions?
Yeah, there's a question. Let me unmute there too. Yes. Okay. A question from Twitch, which is from Chantilly Cake. For someone who wants to learn machine learning or AI, what resources would you recommend?
Well, the way I did that is, first of all, there are lots of courses nowadays in Coursera. I don't know what else, Udemy, that you can use to get your feet in the door, so to speak, to get some, at least to understand, to have some practical exposure to machine learning world. What they will do in these courses, they will teach you how to use a lot of these standard tools like scikit-learn, pandas, numpy. Not so much Rust, because Rust is still not the thing in data science and machine learning. But after that, what I recommend is to you either need some kind of real projects or teams where you will work with someone who have been doing machine learning for a while to practice the standard approaches and methodologies that people use to feed the data, to find the parameter, to estimate, to do the to compare models, to evaluate models. So that takes a bit of a practice and time, and also good understanding of linear algebra and probability, and not so much optimization theory, but I would say linear algebra and probability theories are very important for machine learning in a lot of scenarios, because just for example, you might be tempted to use the logistic regression or linear regression, these methods that I've described today, on in some scenarios where some models, they have some assumptions that you need to understand in order to do a great work, to find the the model that fits your data but the best.
Awesome. Thank you. Any other questions? All right, Vlad, thank you so much for giving this talk. This was really great.
Thanks for hosting this presentation.
All right, we have another talk coming up next month at the beginning of the month, and then after that we have no speakers lined up. So if any of you want to talk at the Denver Rust Meetup, it doesn't even matter if you're from Denver or not. We're completely remote these days. We'd love to have you speak. So send me a message through any of the ways that you can find me online. If you're in Denver, you can find me on the Denver Devs Slack team. Otherwise, you could find me on Twitch or Twitter at like Brooks_Patton. But with that being said, I hope that you all have a great rest of your night, and we'll see you next time. When will the next meetup be? Let me find the schedule really quickly. Wednesday, March 3rd. So almost a full month. All right. Have a great night. I'm signing off. I'll see you next time. Bye.